Good morning, champ. Today we're diving into the world of hydrostatics, the study of fluids at rest. It's where Newton's laws meet pressure, and everything from submarines to the atmosphere suddenly makes sense. We'll derive the fundamental equation of hydrostatics, build up to Stevin's principle, connect it to Archimedes' principle, and finish with a few symbolic applied tasks that tie it all together. Let's get into it. Picture a tiny cube of fluid floating motionless inside a larger fluid. Since it's not moving, acceleration is zero, so all vertical forces must balance. The pressure at the bottom pushes upward, the pressure at the top pushes downward, and gravity pulls the cube down with its own weight. Setting the net vertical force to zero gives a simple relation. The derivative of pressure with respect to height equals negative rho times g. That's the fundamental equation of hydrostatics. Pressure increases downward because each layer of fluid supports the weight of all the layers above it. If the fluid density is constant, we can integrate that relation between two heights. The result is simple. Pressure 2 minus pressure 1 equals rho times g times the height difference. That's Stevin's principle. Pressure difference depends only on density and vertical distance, not on container shape. No matter how weird the vessel looks, at the same depth, the pressure is identical. Now imagine a solid cube completely submerged in the fluid. The bottom face is deeper, so the pressure there is higher. The difference in pressure between top and bottom produces an upward force, the buoyant force. Its magnitude is rho times g times the submerged volume. And that's Archimedes' principle. A body immersed in a fluid experiences an upward force equal to the weight of the displaced fluid. That's why ships float, balloons rise, and you feel lighter in water. Let's take our reasoning to the air for a moment. We start again from dp by d, z equals minus rho g. But for gases, rho and pressure are related by the ideal gas law. Rho equals pressure times m sub a divided by r times T. If the atmosphere is isothermal, meaning constant temperature, we get 1 over pressure times dp by dz equals minus mag over RT. Integrate that upward and you find that pressure equals pressure naught times e to the power of minus magz over RT. That's the barometric height formula. Pressure decreases exponentially with altitude. We'll stop here for the theory. Here's the workflow for every hydrostatics problem. Pick a control volume, identify all the forces, pressure, weight, and buoyancy. Apply the sum of forces equals 0. List your assumptions clearly, then solve symbolically before plugging in numbers. Hydrostatics isn't about memorizing equations, it's about seeing which forces matter. Now for our first application, two liquids of different densities, ρ1 on top and ρ2 below. A cube of side length L and density ROC floats at the interface. Part H1 of its height is in the upper fluid, and H2 equals L minus H1 in the lower. Force balance gives ρ1 times H1 plus ρ2 times H2 equals ρc times L. Solving that, we find H1 equals the fraction of ρc minus ρ2 divided by ρ1 minus ρ2 times L. The depth of immersion depends only on relative densities, not on size. If the cube's density lies between the two fluids, it floats exactly at the interface. Next, let's take the same reasoning upward into the sky. A rigid balloon of volume V and empty weight G is filled with gas of density RHOG. At the ground, we hold it down with a force Fs, then we let go. Now we go underwater. A liquid's density decreases linearly with height. Rho of z equals rho, naught times open parenthesis 1 minus beta z close parenthesis. A rigid bubble of volume V, gas density ratio G, and envelope weight G rises until forces balance. At equilibrium, G times V times the quantity rho of H minus rho G minus G equals 0. Plug the density law in, and we get that the equilibrium height H equals 1 over beta times open parenthesis 1 minus the fraction of RHO G plus G divided by GV all over RAO naught close parenthesis. The bubble stops rising where the lighter upper layers no longer provide enough buoyant lift to overcome its own weight. The key relations we met today are these. dP by dz equals minus rho g, that's the foundation. Delta P equals rho g delta z, that's Stevin's principle. FB equals rho gV, that's Archimedes' principle. And pressure equals pressure naught times E to the minus Z over H. That's the barometric law. The three applications, the cube, the balloon, and the bubble, are all just clever variations on the same idea. Balance of forces in a pressure field. So champ, that's hydrostatics, the art of keeping pressure in perfect balance. From still water to floating bodies to the thinning air above, it's all the same principle. Forces in equilibrium. Keep that curiosity alive. And remember, in fluids, the pressure's always balanced when your assumptions are right.